limited if we don't also do all the other pieces. And I recognize that I'm kind of in the green section as well, but I do think that we have a lot to think about, not just in terms of knowledge, scientific knowledge, but communication and policy making around open science. Starting to zoom in a little bit more to the United States and our federal agencies. 2023 was declared by the White House to be the year of open science. There is a good Nature article if you want to read more about that, and there's also a White House announcement. I would say of federal agencies, NASA is kind of at the forefront of this effort with their Transition to Open Science program, or TOPS, and they've been inspirational to us. But within NOAA, we're starting to build up from the ground up more of these open science types of groups and practices. And the thing I'm going to talk about today, FIMS, with the logo on all the way to the left for you, is one part of what we're doing at NOAA Fisheries around open science. We also had a number of folks go through the OpenScapes program recently, and that's going to be continuing for the next 3 years. It's sort of a mentorship and community building program to make science more open. Catherine Doring on my team is the lead of the NOAA Fisheries Integrated Toolbox, which is meant to be an open repository and one-stop shop for ecological, economic, and protected resources modeling. And then we also have a really active our users group within NOAA Fisheries that has started to do a lot around knowledge sharing, training, that runs kind of periodic webinars, as well as gathering kind of like-minded folks and people who are all using similar tools to help share and learn from each other. And so we've started to bring these together under this NIMS OpenSci GitHub organization. I think we're trying to become more organized like NASA is and have kind of one major umbrella at NOAA Fisheries that runs these open science initiatives, of which FIMS is one of them, but it's certainly related to and keeping in good communication with the other ones. So what is FIMS? I want to be clear that it is not a single model, but it's built to be more of a suite of interrelated software tools. And so for the R users in the audience, I sometimes think of like the tidyverse or the tidy models within the tidyverse, and that they're not all the same model, but they use similar grammar. So it's kind of easy to move from one to the other. At its core, this is really the open science approach to fisheries stock assessment. But we also want to make it easier to build bridges to ecosystem, climate, and economic models and data with FIMS. The main differentiator between this and existing systems, I would say, is its flexibility. It's meant to be more innovative and able to adapt into the future. We can try to build the best model of today, but then we know 20 years from now it's going to be out of date. So we really want to build it with the idea that it's going to continue to change. And in order for it to continue to change, it has to be a collaborative community effort, because developers are going to move on. New students like yourself are going to come on and be the next generation of developers. And so we need to make sure that it's something that is not all centralized in one small group of people or contributors. And building it in this framework will allow us to address numerous NOAA Fisheries priorities that I'll get into later in the talk. So I'm going to get more into a little bit about the motivation for reproducible and reusable code. In this kind of code quality continuum, I would argue that we in the past in stock assessment world have been maybe into the orange, pretty squarely in the red. So the ease of modification is the x-axis. This is sort of how easy it is for you or any other collaborator to pick up this model in the future and use it and edit it. And then reproducibility on the y-axis is whether it can run in other places. So when I was here at SAFS, I wrote my first model for my PhD. And I would say I was squarely in this like lower quadrant. I can write it and it works for me. And that seemed like the right thing to do. That's definitely the fastest way to write a model. I thought, okay, I just want to get this chapter done. I just want to get it published. I never need to run it again. So I'm just going to do it as quickly as possible. Well, it turns out when you actually publish a paper, you probably do need to run it again when the reviewers get back to you and they want you to change a whole bunch of stuff about it. And so I already was kicking myself for being in this lower quadrant when I got my reviews back, because I went back to it several months later and I could not read it. So that was bad. And then I thought, okay, well, I'm not going to invest the time to make it better now, because, you know, I'm just going to address these reviews and then I'll submit the paper and it'll be published and I'll never have to run it again. Then I get an email from a colleague. Hey, I've got some New England data that I would really love to run your model on. Can you send me the code? So I send her the code. And in this case, you know, this is by a software engineer, so it's QA team, but that I'm going to call that my collaborator, that second row up from the bottom. She looked at it and said, this isn't working on my machine. I'm going to rewrite it in Python. And so she rewrote it in Python and wrote her paper that way. Fast forward a few years, now I'm part of this ICES working group, and they want to rerun this model again on a whole bunch of fisheries data from all over the world. And so I've rewritten it again with Sean Anderson in the STAN programming language. And so I could have saved a lot of time if I had not started so far in that lower left-hand quadrant. Now I would say that model particularly is in the yellow, and that it's an R package, it's on GitHub, you can install it. It seems to run for at least a couple of us within the working group, but it took years to get there. And I would argue that even if you're not going to be writing something like a stock assessment model that's going to be reused over and over again for management, there's still benefits even for just scientific publications in starting to move away from this lower left quadrant of the code quality continuum. It is possible to go too far, as illustrated by this XKCD comic. So in this one, you ask someone to pass the salt, they don't respond, and it's because instead of just passing the salt, they're actually developing a system to pass arbitrary condiments. But it may take a while at first, but it'll save time in the long run. And so this opposite end of the spectrum is often referred to as over-engineering, and it's also not good, because then you're spending so much time and effort to not satisfy goals that the user actually has. And so the sort of biggest problem, I would say, in doing FIMS has not been, you know, how do we move from where we are to a somewhat better engineered software? It's more, what is the level we're trying to target? We probably don't want the system of arbitrary condiments. We don't want something that only runs on your computer that no one else can ever modify or run. And so we want to be somewhere in the middle. So in this one, I've changed the axes on you. The x-axis is the level of software engineering. And on the y-axis, we've got both ease of reuse and difficulty of maintenance. So as you make something easier to reuse, it also becomes harder to maintain. So there's a trade-off here. I would say right now we're kind of more in the hard to reuse but less software engineered part of stock assessment modeling. But if we go too far in this direction, we end up over-engineered. And there's a sweet spot. It's similar, I think of this as kind of that model complexity diagram that many of you have probably seen. You don't want it to be too complicated. You don't want it to be too simple of a model. And the cycle here represents, I don't think we're going to hit a bullseye on the sweet spot of engineering with FIMS in the first go. We're going to circle it. Or you could think of this as like a Kobe plot where you're like trying to hit not overfished, not overfishing, but you're probably not going to hit the exact right F. You're going to kind of go too high, then go too low, and hopefully get closer and closer to the middle. So that's where we are with FIMS. So this is sort of another way of saying what I just said, which is that there's one reason to make FIMS, which is that we need a better way of maintaining, customizing, and evolving models. Another thing I haven't really talked about yet is this kind of right side. We also have a lot of models that can only be run on personal computers, or they can be run in the cloud, but they're not really built to leverage cloud capabilities. And so as computing continues to evolve, that's another reason why we need to evolve our models. The other reason, of course, is that the dynamics of an individual fish population are not independent of the climate and ecosystem that is around them, or the people that are fishing them and depending on them. And so we need a way to better model this within our systems than what's currently available in most stock assessment modeling software. So this is going to move us towards a more integrated and interdisciplinary approach, largely due to its flexibility and scalability, its ability to evolve and connect more parts of the ecosystem, and the fact that it's not just a few people maintaining it, but it's meant to be more open source like in terms of its development and maintenance. And so who are these people that are developing and maintaining FIMS? Sorry, it looks like the middle box is cut off. I thought I fixed that, but it's not showing up right. The implementation team, it should say it has representatives from headquarters, that's our team, regional science centers, as well as interdisciplinary experts. So this is kind of the core developer group within NOAA Fisheries. But we're kind of trying to get input from a lot of other places along the way, including NOAA Fisheries leadership, internal partners, folks who are doing that kind of open science work that I mentioned earlier, as well as the Climate and Ecosystem Fisheries Initiative. And then on this side, we have the FIMS Council, of which Andre is the chair. And
thank you very much.
Composed of academics like Andre and fishery council members also like Andre, and international groups, which arguably you could also be an international group. But not just him, there's also other people from fishery management councils. I'll show you more of who's involved in that along the way. And so the idea here is we want to maintain communication with all these different pieces so that we are incorporating feedback throughout the whole process and kind of at the end, instead of the end, which has kind of been typical of modeling approaches in the past. So our implementation team of co-authors, as I mentioned, there's a couple of us over at the Office of Science and Technology at headquarters, subject matter experts in fisheries and ecosystem modeling, and then a number of regional and subject matter experts. There's 2 representatives from each region of NOAA Fisheries Science Center. In the past, we've seen a lot of these models tend to be kind of developed and then stay at one center, and people go talk to the people down the hall who know how the model works. And so we really want to make sure that we're bringing in regional perspectives from the beginning so that we're not just meeting the needs of one region, because they're all pretty different in how they do their management. Within the council, as I mentioned, we've got representatives from Europe, Australia, New Zealand, the Pacific and Mid-Atlantic Fisheries Management Councils. And then we want to not just operate independently of all these other initiatives at NOAA that are trying to be more open science or trying to be more ecosystem integrated, that have been kind of going on for a long time. All right, so that's sort of the introduction piece. I think from now on, if you have clarification questions, I can pause and take those. I don't want to get too stuck on the introduction. One thing I want to talk about is the software development lifecycle. And so the idea here is that implementation, which is number 4, is just one part of this cycle. So there's quite a lot of planning and design analysis that goes into thinking about the software before we actually start writing it. And then after we kind of do one iteration, we want to make sure that we're building in time to plan based on the feedback we're getting after the first sort of go around of this cycle. Right now, I'll say we're in the testing and integration phase of the first cycle. And so we have most of the model is all the separate pieces of the model are built. We're trying to hook them all up, fix any bugs that we're finding through testing. And then we're very quickly going to get to the point where we can run a benchmark against other stock assessment models before we go and add a whole bunch more complexity to the model. And so to zoom in on that a little bit, we're planning to finish this development milestone testing and integration phase in April. We've got a quality milestone that'll go into the summer where we can kind of go through and fix all those sort of messy things that we've done in our hurry to get everything working. Around the same time, we'll be rolling this out to different regional representatives who can try to get it running on their local stock so that we get some feedback from the community while we're still doing development. And then we start planning for the next iteration. And so planning, when we first started this across our group of the implementation team, we brainstormed 287 requirements. And requirements can be functional requirements, which for a stock assessment model could be like, it must estimate, future catch so that we can set policy. There's also non-functional requirements, which are how it's going to do that thing. And so it should do that thing in a relatively fast amount of time. It should be usable by the average scientist, should be easy to install, things like that.
Wasn't really a requirement. How did that happen?
Well, one set of the requirements are functional forms. And so you get like Lorenzen mortality or Thorson's function to do whatever. So I don't know which of Thorson's things are one of those requirements, but that's some of the requirements are things like that are named after people because they're functional forms that they invented or popularized. Spatiotemporal is also there, is pretty large. So it's definitely some Thorson influences here. Then there's also business requirements, which are things that the customer needs. And in this case, the customer is the Fishery Management Council. So even if it's the best ever model for scientists, it's not going to be fully fulfilling those requirements if it's not doing the thing it needs to do, which is be used to manage fisheries. So a lot of these are words that are obvious, like parameters and model, but you can see there's also really big things that are not in a lot of the current assessment models, like prey or spatiotemporal. And so I think the reason this word cloud is to show that we're trying to capture the requirements of today and also things that we don't currently have that we want for the future. We ranked each of the requirements according to impact, effort, and compatibility. Impact is sort of how important it is to do the thing. Effort's how long we think it's going to take. So that's worse if it's higher. And then compatibility is how much we need it to meet our current terms of reference for the Fishery Management Council. And so this is sort of hard to quantify, but I just wanted to show this violin plot to discuss the types of requirement groups we came up with, which are user and developer experience, parameterization, outputs, model structure, forecasting, and fitting estimation and simulation. And a lot of this stuff like fitting estimation and simulation is high because we need to do it to be compatible, and it's relatively low impact once you actually have a model that's fitting. Whereas the user and developer experiences spans things that could be really high impact or not that high impact, and that can be hard or easy to do. As we were going through these requirements, though, we realized there's sort of an unspoken requirement that we need to focus on initially, though, which is that most fisheries management councils require that you bridge new assessment methods to old assessment methods. So you can't just come out of the woodwork with a new model and say, okay, now we want you to switch from using stock synthesis to our new model. You have to first prove that you can put the same data in and get relatively the same result out. And if you don't, you can explain why. Luckily, we had this project that Bai Lee on our team had just run, the model comparison project, which is published in Fisheries Research. And she actually took 12 different operating models and compared the 4 assessment models that are primarily used across the United States for management, along with a lot of partners at different regions. And these are AMAC, ASAP. AMAC's used in Alaska, ASAP is used in the Northeast, BAM is used in the Southeast, and then stock synthesis is used all over the world. And so we realized if we just made FIMS another model on this graph, we could do a lot in convincing people that it was actually able to replicate previous assessments and maybe try to make our cases to the council a little bit more broadly. So that's sort of what we targeted for the end of milestone 1 is, and the other thing that Bai did as part of this is she really succinctly identified sort of the common pieces of these 4 different models, which was a good target for us. Okay, a big part of how we've been able to run such a large project has been around team organization and GitHub management and project management in general. So I'm going to talk a little bit about that. This is the landing page of our GitHub organization. And so this is meant to be kind of, and you can go there on this is the link up here. You can view the project status, view all the documentation. The project documents are only going to be available for NOAA folks. And then you can also view our collaborative workflow doc that talks about, you know, if I wanted to become a FIMS developer, what do I need to install on my computer? What are the processes for checking out a branch, adding my feature, and then merging it back in? We've had to do a lot of training. So our group has spanned people with lots of different types of expertise. Some of them are more software development types. Some of them are more ecologists or managers. So we've really done a lot of training on everything spanning template model builder, TMB, R package development, C++ coding, how to use GitHub, how to use our development process with different branches, how to conduct a code review. And so those were sort of formal training courses that we did at a workshop in March. And then in addition to that, there's been a ton of on-the-job work. There's only so much we absorb for sitting through a couple-hour training. And so what's been really crucial for us are these buddy coding sessions, which we've been doing using Visual Studio Code, which has a live share feature that you can kind of all simultaneously edit code live and run it, kind of like a Google Doc. So we've been using that really heavily, along with GitHub Code Spaces, which allows you to set up a cloud-based integrated development environment that everyone can log into at the same time, make their changes and push them up, and then they're live on the web. And this is really helpful, especially at NOAA, where you need IT to come install things on your computer, that you don't have to do that. You can just open a web browser and it's got everything you need to run FIMS and compile FIMS there. I will say code spaces, you have to pay for the development time you use. It hasn't been more than like $12 or $20 a month for us, but VS Code is totally free, the live share, so you don't need to pay to get access to that. Another really crucial thing has been having a really clear and pretty strict change management process. And so we used what's called a scaled trunk-based development workflow, which means we do all of our development on feature branches and sometimes sub-branches of features. And so the main branch is always able to be compiled, always able to be installed, and it's always passing our test cases, so that when we're adding new stuff, we can do that simultaneously on different branches without blocking another group, because we're breaking off into kind of smaller groups for each adding different features. No one has permission to put their code directly into that main branch, not even me. And I would have been lazy and probably messed something up even myself if I had given that permission to merge into main. So I'm glad that I blocked even myself from doing that. So I need someone else on the team to approve the code that I've written with a code review. Before they do that, they have to make sure there's a test case that someone can run that passes before it gets merged into main. There has to be documentation on that new code. We didn't have that one as a requirement for a while, and then we were getting all these documentation errors. So now it will actually throw an error if you do not have a documented piece of code, because that was the only way we were able to force, again, people, including myself, to actually document their code. All GitHub actions have to pass. And like, you have to have a teammate look at and approve the code. And that has double benefits. I think the benefit of, you know, not checking that you've done made a careless error that another person can see. But it also helps people know what you're doing. So there's never any change to the code that's made that at least 2 team members aren't aware of, that have read and reviewed and looked at it and know that that change has been made. And so it's like also helping us learn the code and keep on top of what other people are doing. Every week we triage issues or bugs, and we decide, are we going to do them now? Or are we going to do them later? Or are we going to try to do them during this quality milestone we're going to do in a bit? And so all these actions create badges on GitHub that are all hosted on that kind of a sub page of that main landing page. You can see now that we're getting close to wrapping up milestone 1. There's not as many open issues at milestone 1. We're moving them to milestone 2 as much as possible. And you can see that, you know, command check is passing, so you can still install it and everything. So it's really easy to see when something goes wrong. Yeah, Mark.
So who's managing your PRs, and is that still you after somebody else has dealt with your checklist here, or each individual team members doing that? You still have a czar basically?
Anyone can merge it in, so it's not just me. I do weekly. I'm in charge of the weekly issue triage. So if there's like a PR open, then I look at it at least every week, but other people can also merge it in. It's not just me.
Yeah.
Good question. And yeah, I mean, like I said, there's a different level of software engineering that works for each project. I don't think this level is going to work for your average PhD chapter, but for something that has so many people involved at NOAA, it's sort of the right level we're targeting right now. So GitHub Actions have also been a really key thing. They're automating the routine tasks that we need to run, and they're all running, you know, on GitHub, so we don't have to do them locally all the time. So we're always running command check. We have automated actions that format the C++ and the R code associated to our style guide. So everything's always being formatted consistently, and it'll throw an error if you've used kind of the wrong C++ syntax or anything like that. It's automatically generating HTML pages for our documentation based on the comments that people are writing into the code. And we also have one that creates a PR checklist. And so if you're a reviewer and you get a new code review coming in, there's a checklist. You can go down, okay, have I looked at the formatting? Have I made sure that everything's documented, in case you're kind of forgetting what you're supposed to be doing as a reviewer. Catherine Doring has been really great, particularly because she's kind of an expert in GitHub Actions. And, you know, as we go through the development process, again, we're learning, okay, we had this one running anytime we push to any branch, but maybe that's excessive. Maybe we should only run it on a push to main. So we're going through and changing these based on our experience real time. Okay, I'm going to go into the actual package structure now. So FIMS is an R package. Like many of the most complex R packages, it's got C++ bits inside of it, but the average user wouldn't ever need to look at those. They could just run it in R. However, the R code is sort of the last piece that's coming online because we first need to run the full model before we have the code that can deal with the processing of the inputs and outputs and everything. The bulk of the actual math is going to be in the inst include folder. We use template model builder, or TMB, to estimate, as well as use statistical distribution functions. We don't want to rewrite those from scratch if they're available in TMB. I think TMB has just rewritten the R ones, or imported the R ones. And then we use the RCPP package so that all of those C++ components are individually callable from R. So you don't have to call it through TMB. You could also just say, you know, I want to get the expected values for my von Bertalanffy growth function in R, and you could do that without running the full model. We also automate testing both through Google tests and compile tests on C++ and using teststat in R. So if you go to the actual package repo, it's got a lot of the folders that you might be familiar with if you've done any R package development. The R folder, inst, source, description. The README has some of these badges that I pointed out before. I should mention this slide was made by Andrea, my colleague. So the source folder really just has this very small fims.cpp file that actually is used to compile the model, but the bulk of it is not in source. The description file tells the linker that it needs TMB, RCPP, and RCPP eigen to run. And so because we've got this FIMS package.r file that has all of the imported files, as well as the need to use this dynamic library, it's actually adding that when you run Roxygenize to document your R code, it's registering this FIMS library, and that's what actually creates the DLL on your local computer when you install it. So you don't have to think about compilation or install. It just happens when the package is installed for you. So if you go and do, remotes install GitHub FIMS, that'll all have, the DLL will be created in your local library. You don't have to worry about compiling. If you go into inst include, which is where as I said, all the math is, there's 4 main folders: common, distributions, interface, and population dynamics. Common sort of the common files. Well, common distributions and interface are kind of self-explanatory. Population dynamics, there's a lot of subfolders under there about growth, maturity, recruitment, all that stuff, where you can see the actual math. And it's all separated out into individual modules so that it's easy to kind of add new pieces and swap them in and out. I mentioned code spaces, and I think some people seemed interested in that. That's all configured in this .deb container file in the GitHub repo. And so if you set that up with a JSON file and a Docker file, that's what allows you to then get this really nice code spaces environment. You pick that code drop down from GitHub, it'll allow you to open or create a new code space where you can develop in the cloud. And you can do this on the free instance. It's just at some point, the capacity of time that you have to run is pretty limited. So you can do this even if you don't have a paid GitHub account. Yeah.
Oh, just what do you guys use for a license?
Oh, I think we've used the GNU license because we have some code. I'm trying to remember if we just depend on TMB or if we have some copy code there. GNU is a copyleft license, I think. So if you're going to reuse any open source code that uses that license, you need to also use that license. Otherwise, you're violating their open source terms. And I think we have enough dependencies that we've had to use that license as well.
And sorry, NOAA is okay with that.
There's a whole working group trying to talk about that right now. That's what we're going with for now, but they may recommend something different when they come down, and then we'll comply with it. They'd previously been told to use the Creative Commons license, and so that's sort of the internal debate we're having is GNU versus Creative Commons. And there's some weirdness about there's some weirdness about that I think probably a lawyer would be better qualified to speak on. But yeah, for now we're using a copyleft license. So right now, if you wanted to run FIMS from R, this is sort of what your R script would look like. You'd have to install RCPP and FIMS. Then you'd have to load FIMS as a module in RCPP. And then once you have this FIMS object in R, you can add all the different parts of your model, like what kind of growth you want, what kind of recruitment you want, what kind of selectivity you want, the parameter values, bounds, those sorts of things. And then at the end of that, you would call, run FIMS. So the benefit of this is that it's easier to swap in and out if you set your selectivity to be, selectivity fleet 1, and then you think, oh no, I actually want to do a double logistic selectivity or some other type of selectivity function. You can just reset your selectivity without having to muck around in any kind of manual file editing. This is still a lot if you think about all the things that go into a population model. And so I think eventually we want to get to the point where we have a lot of wrapper functions, like some function called like create FIMS model, that you just give it some input values and it'll set it up for you. So that's where we're going. But right now you kind of have to manually set it all up for yourself. But again, that R piece is going to come in a little bit later.
How does that link to estimation? If you're selecting components, does FIMS do the linking between the components?
Yeah, so there's a function that called add to FIMS TMB. And so it goes through that list of parameters that are coming in from R via RCPP, and it's adding them all to the TMB tape. So that when you call make AD fun, all of those parameters are registered. But it's a little bit different than like if you run a TMB model now, you have a list that goes into make AD function, like parameters equals, and that list is full of stuff. And now we're essentially setting all that up in C++. And so we're having to write another function that then says, if you want to look at what your parameters are in R, you have to export that list back to R again.
I can see a lot of, it's gonna be interesting to set these models up if you got lots and lots of options.
Yeah,
As, I mean, that's been the worry all along, but I can only imagine the size of the file that you have to write to create all the bits.
do you mean the input file,
Well,
the
the
output
structure,
file?
yeah, basically, I mean, an average synthesis assessment's got, 30 or 40 options that you're choosing, right?
Mhm.
Without getting into the 50 fleet model where you've got, so just thinking about how you illustrate, how do you summarize that for, particularly for, I'm thinking as a reviewer, I
Yeah.
really don't want to read through 1,000 lines of R code.
Yeah, no, yeah, and I think we're going to have R code as well as some sort of input file that summarizes that. And even if you're not ever, using the input file to run the model, you're at least outputting it so people can like look over their configuration first. We're also hoping to have a lot of, and again, this is like further down the line, some plotting functions that can summarize that model configuration for you. Like if you've looked at Jason Cope's Shiny DL tool, I've been really inspired by that in terms of like, okay, before you even run the model, you can visualize sort of what all your functions are, where the data are going. And I think it's helpful to do that visually in an HTML file as opposed to, in R code or in a text file. It's harder to look at. So we have ideas, although we haven't done it yet. It's definitely a lot of work coming ahead. Yeah, so in terms of things we're learning from this process, I think the importance of training, particularly how we train new developers as they come on board and off board of the team, because it's going to be a long running project. So we're going to have turnover, has been really important. This ability to do these live coding sessions with code spaces and live share has been really important, as well as the GitHub change management process. Things I think we are still figuring out how to do properly is, I think the scientific review process is really built around, you finished a thing and here is a whole paper that I can look at and review and know exactly what you've done. So we want to incorporate that early feedback, but there's sort of not a clear structure of how you evaluate things that are in progress and things that are not quite done. And so still trying to think about the best ways to do that and engage with stakeholders early on in the process. Finally, our cross-discipline experts are crucial to the process, but they've also had difficulty. Right now, we're pretty deep into the stock assessment weeds, and so we're finding out how to re-engage those experts and get their input and their understanding of the types of data that they're going to have early on is something we're working on. So kind of zooming back out, I think this is a cultural shift in terms of how we build scientific software. This is a slide from one of the NASA Transition to Open Science programs presentations. So in addition to sort of all the software stuff they're changing, they also have these policy directives that I think are going to be really key to actually transitioning them to an open science environment. Like you have to share your software at the time of publication or the date of funding award. And there's actually an executive order I'm not sure the scope of it, but it applies to a number of federal agencies. So this is actually a mandate now that we have to share our software. And then the other thing that NASA has that I don't think we've implemented at NOAA yet is that anything that is funded has to include a software management plan. So it's not enough to say, I wrote this model and it's going to live on my computer forever and I'm never going to share it, or I don't have ways for people to contribute. You have to build that in. And I think that that's the way that things are going, at least within our agency and within NASA. And so it really feels like we're on the cusp of sort of a new approach to science, which is exciting and also daunting for people who are trying to learn all these skills. But I don't see it going back the way that we're seeing this come through both at NASA and at NOAA. And so again, just bringing it back to this UNESCO diagram, I think that the open knowledge piece is one part of it, but those policy directives, the communication, and there's actually a summit, I'm not sure if it's open, I think it might be publicly open, on this UNESCO open science approach next week. If anyone's interested, from the 8th to the 10th, on sort of sharing approaches across countries and across agencies of how we're all doing this. Because there really does need to be more communication built in addition to all the software pieces. And with that, I think one thing that I'm thinking about is how do we make it so that we can engage with new developers in the future? I don't think we're quite ready for it yet as we're working on this initial benchmark. But if folks have questions or comments on this, I think I would really love to hear from, as a student or as a postdoc, what would you need to feel like, hey, I'm going to do this project where I want to test out a new function for doing something. I'm going to do it in FIMS rather than writing my own code. Like, how would you best be supported to learn that and get onboarded? And like, if you have any thoughts about how we can take contributions from the community and incorporate them more, because I know a lot of the cutting edge stuff is happening in universities, and we want to be able to better partner with universities when we're trying to update the model and making it more current and more incorporating new approach, and also creating sort of a platform for testing out new approaches. And similarly, if you have any feedback, if you've clicked through any of the website links I've shared on sort of if you're having trouble finding anything, or if there's a way we could better communicate where we are and what we're doing. Yeah, so with that, I don't have anything else if we want to open it up for questions, comments.
Great. Thanks for such a great talk. So we're going to go ahead and take questions for 10 minutes. For about 10 minutes. So for anyone online with questions, please enter them in the QA box and we will read them aloud. And for any questions in the room, feel free.
We have a question online from Emily asking about what's the solution for the JSON input files?
It's kind of a broad question. Not sure the solution is how they're written or read or structured. We do have.
He said as in the IO part.
As in the IO part. Okay. Well, we have a early on in the process, we had a sub-team spinoff and sort of talk about designing the inputs. And they decided that the best way to do that is to create a object class in R. I can't remember if it was an S3 or an S4 type object class called a FIMS frame. So it's a specific data frame structure in R that has some validation built into it. So if you go and put in, a bunch of inputs and you're missing something, you'll get a warning back right away that it's not right. And so from that, I think you would use the JSON light package, once it's been validated and everything, to write it out into a .json file at the same time that it's run through the model. So there's some sort of archive. So there's some sort of saved record for reproducibility of the JSON input. And then also, it's able to use the stuff that's already built into the S3 or S4 class to validate that the structure is correct. And also, we were really inspired. I was really inspired by the unmarked package, which is for mark recapture data modeling. They have a bunch of different data frame types that sort of all inherit from the same base type. So I think like as we add more capabilities to FIMS, we would use that as a model where there's some sort of FIMS frame that's the parent type, but you could have like FIMS frame age, which is the one we defined, which is an age structured model. You could also have FIMS frame biomass dynamics or something that had a somewhat different structure if you're using a different model structure.
Thanks.
I don't know, I mean, I'm obviously aware of some of what's going on. But I guess, and I'm sure we talked about this, the sort of challenge when you're creating models is the end matrix. But at the end of the day, the difference between production model and an A-structure model and Atlantis model is N. And I guess my question is, how are you, and maybe I'm just not smart enough to see it, but how are you able to keep that dimensionality, A, under control, and B, link it into, let's just take selectivity. I mean, with our size structure model, we've got selectivity in principle by sex, the function of length, whether you're mature, whether you're immature, I know how it's done in like parcel, which has the, that sort of textual linkages, with, I presume, some code to check if you've got all the bits specified. But how are you envisaging that? Because I know right now we're focusing on age structure models, and those are relatively straightforward.
Yeah, I mean, there's definitely going to be some retrofitting we'll have to do when we expand the scope. Right now in FIMS, there are no matrices. Everything is stored as a vector. So if you're going to index, it's called dimension folding, I guess. If you're going to index something by year and age, you need to, do the algebra to calculate whatever your dimension folded index is that returns year age. So we have some data structures that are year age. We have some that are year age fleet. We have, and I imagine at some point we'll have year age length, year age length fleet. And so that's both helps make the dimensionality problem more flexible, as well as is faster in C++ to access vector objects and not matrix objects. But we have also been really influenced by the CASL2 and the way that they've structured that. Right now, it's sort of all discrete in that someone on the team put it really well, like there's like a grid of year and age that you're stepping through all the time. And so we really want to move in the future to a flexible timing approach like CASL2, where you're not just, going year by year, but you can just specify continuous time increments and only like match to the observations that you have in continuous time. But so we've sort of set up the architecture to do that, but we haven't tested it yet.
Is that causal to the one that doesn't work? As opposed to causal, which doesn't work. There's a lot in causal too that's really cool.
There's a lot in CASL2 that's really cool. And so we're chatting to them about what worked well for them and what did not. So we've got an open dialogue with that development group, but we're not doing exactly everything that they've done. Has been our approach. I'm sorry, I don't know anyone's name. I think you were first.
Oh, I'm wondering, because you talked about a lot of ideas of with your group, things you're doing to kind of make your code really usable and reproducible. What are there some ideas other than just write better code that we could kind of take as students or as lab groups kind of from the software engineering world to help us write better code?
Yeah. Oh, I realize I'm supposed to be repeating questions. Hopefully you heard Andre. But I think the question was, what would be our advice for grad students beyond just write better code to help them as they learn and write and develop packages and software? I think if you're an R user, Jenny Bryan and Jim Hester have a website that's like things you've never learned about R. That's all about how you do path management and setting up a project-based workflow, they may call it now. That was really helpful for me as a grad student. That was sort of where what started down this reproducibility hole. Another part I think that's been sort of basic has been really less technical and more social. Like if you are going to work on code with a buddy, that is something that helps. Just not only you're sharing but it also helps you write better code. I found like there is something called rubber duck debugging, which is you just have a rubber duck that you tell what you're doing, and just saying it out loud makes you figure out what you did wrong. And I found that too with my collaborators. Like I'll start writing an email being like, so I'm doing this thing in FIMS and it's not compiling and I did this, this, and this, and I never actually send the email because by the time I've actually written down my whole thought process, I realize what I did wrong because they're basically my rubber duck. So, and I think like when I was a grad student, I don't know, maybe it's getting more collaborative, but I think the idea is like, you're going to go by yourself and write a giant dissertation without talking to other people. And so the more you can, you know, use your community and not think that you have to do it all alone is something that was really helpful for me. I had a really good lab group and quorum mates who were really supportive throughout that. And then I think also in terms of rubber duck debugging, if you can do things like in an R Markdown or a Quarto or a Jupyter notebook, one of these formats that allows you to write some text, then the chunk of code, and then write some more text and just like notes to yourself of, okay, here I'm going to load the data. Like it may seem like you're stating the obvious, but it's so helpful when you go back to it in 6 months because you may think you're going to remember what you're doing, but if you're like me, you don't. So I don't know, maybe that was all like really basic advice, but that's stuff that helped me in the past.
Probably one more question.
Kind of related to that question, the other side is when instead of writing new code, following all the best practices, you have to take old code or legacy products and somehow put them into your pipeline and update. Like a lot of times you come across an old code that is based on outdated packages and things that have been updated since. Like, what is the kind of best practice in a project like this? Kind of use the latest and greatest, so update everything, even if that's going to take a long time, or teach it with from scratch, or is there value in taking all the information, all code, and just baking that into your new product?
Yeah, that's a great question. The question is about not just when you're starting from scratch writing your own code, but when you're working with dependencies or code that other people have written and putting it into your pipeline, how you kind of get a version snapshot, or if you're always kind of upgrading to the latest and greatest version. Yeah, we've dealt with this specifically with TMB already. There's a new AD part of TMB that we haven't switched over to yet in FIMS. So they used to use CPP AD, they're switching to use TMB AD. We haven't switched yet to use TMB AD because our thought was we're going to get FIMS totally working. We're going to finish milestone 1, and then we're going to switch to TMB AD at a point that we know everything's working and the only variable we're changing is that version of TMB. And so Code Spaces has again been really great with this. That .dev container folder and Docker file allows you to have what version you're using. So right now that's hard coded at some previous thing. And then, or you could do this in a description file, and an R package will allow you to say, I want to depend on this R package version X. It is sort of a hard, and sorry, I should say that dev container file, you can run all that locally. So even if you don't have a code space, it'll still create a local container that has all of the right versions of everything on your local computer, which has been helpful. But yeah, it's sort of hard to, I wouldn't say there's one hard and fast rule for when to always be on the latest package and when to use an older version of a package, because we've had to make, I think with some of the other R packages, we're always using the latest and greatest, and with TMB AD, we're special casing it to use an older version. So I'm sorry, I don't know if there's an easy answer on that other than being aware of which version you're on, and like having something like a Docker file that keeps track of it so that consciously when you're switching, and that, oh, it's that dependency that broke me, not my own code.
So we are regrettably out of time. There are more questions.
I'll be
hopefully
around for a little bit.
just
Yeah,
be around for a little bit. So if you're in person, feel free.
or email me.
Yeah. Or
Oh, I forgot. I should switch to the last slide. So if you're not, thank you. And if you are not here, you can, that's my email address if you want to follow up.
So thank you everyone for coming. Please join us again next week.
Where does forefront come in? Call me down in forefront, call me down correctly.
And there is
I
a
think
class
there's-
in here at 1:30, so.
Oh, okay.
just keep that in mind.